a golden eye hangs in the absolute stillness of the void, a silent sentinel positioned at the second Lagrange point, roughly 1.5 million kilometers from the warmth of the world that birthed it. Here, far beyond the silver glow of the moon, the James Webb Space Telescope exists in a state of permanent freezing shadow. It is suspended in a delicate gravitational balance, a place where the pull of the Earth and the Sun meet in a quiet equilibrium, allowing this machine to stare into the abyss without the interference of our planet's heat or the shimmer of its atmosphere. The velvet dark of this deep space harbour is its sanctuary, a vantage point from which it can observe the very edges of the known and the unknown. Its primary mirror, a vast basin of 18 gold-plated hexagonal segments, glows with a dull, haunting lustre. These mirrors were not fashioned to capture the light that human eyes can perceive. Instead, they are tuned to the infrared, the long and invisible waves of light that have been travelling through the expanding fabric of space for eons. As these ancient photons journey across the cosmos, the expansion of the universe itself stretches them, pulling their wavelengths into the red and beyond, into the heat signature of the past. This telescope is a machine built to remember. It is designed to catch the first heartbeats of existence, the very moment when the primordial fog of the early universe cleared and the first stars ignited in the hollows of the deep. For decades, we moved through the world with a map we believed was nearly finished. This map, known as the Standard Model of Cosmology, or ΛCDM, served as the grand architectural blueprint for the universe. It was a story of elegant, predictable progression. According to this model, the universe began in a state of extreme heat and density, followed by a period of rapid cooling and expansion. There followed a long, silent era known as the Cosmic Dark Ages, where nothing but neutral hydrogen gas drifted through the void. We believed that gravity worked slowly, like a patient sculptor, gradually pulling these clouds of gas into small chaotic clumps that would eventually become the first primitive stars. These stars would then cluster into small irregular galaxies, which would slowly merge over billions of years to form the grand spiral structures we see in our local neighbourhood today. This was the comforting stillness of the old world. We felt we understood the timing of the cosmic clock. We thought we knew exactly when the first light broke the darkness, and how long it took for the first great structures of the heavens to assemble. But as the first data streams back from the golden mirrors at Lagrange Point 2, the reflection staring back at us does not match the map we have drawn. The telescope has pierced the shroud of the cosmic dawn, reaching back 13.5 billion years, and it has found something that should not be there. Instead of the small, messy seeds of galaxies predicted by our theories, the telescope has revealed giants. In the very earliest epochs of time, when the universe was a mere fraction of its current age, Webb has observed massive mature galaxies that appear as bright and complex as those in our modern sky. They are the universe breakers, structures so large and so well developed that they defy the laws of cosmic evolution as we have written them. It is as if we have walked into a nursery and found a group of fully grown adults sitting among the cradles. We are standing at the threshold of a discovery that suggests a structural impossibility. This is not a minor discrepancy or a smudge on the lens that can be explained away with a simple adjustment of our equations. It is a wall of data that crashes against the shores of our most fundamental theories. The presence of these impossible giants implies that the universe matured at a rate that our current understanding of gravity and dark matter cannot account for. It suggests that there were forces at work in the beginning that we have yet to name, or that the cosmic clock was ticking with a ferocity we never imagined. This telescope is no longer just a tool for observation. It has become a bridge between the present and a beginning that is far stranger than we dared to suppose. Every photon caught by its golden segments is a whisper from a reality that contradicts our textbooks. We are forced to confront the possibility that our understanding of the cosmos is not just incomplete, but fundamentally flawed at its core. The silent sentinel at the edge of forever has looked into the dark and found that the story of our origins is not a simple tale of dust turning to stars, but a complex mystery that may require us to rewrite the history of everything. The wall we have found is not a dead end, but a confrontation with the limits of our own intellect, a signal that the universe is far older, far more complex, or far more radical than our maps ever allowed us to believe. We are the universe trying to understand itself, and for the first time, the universe has told us that we are wrong. The human obsession with a predictable sky is as old as the first campfire. Long before the first glass lenses were polished, or the first equations were etched into parchment, the gaze of our ancestors was fixed upon the rotating vault of the night. To those early observers, the heavens were the ultimate expression of permanence and divine order. The stars moved in perfect rhythmic circles, a celestial choreography that suggested a clockwork mechanism fashioned by a master architect. This was the ancient dream, a universe where every gear and lever followed a simple, elegant, and unchanging set of rules. For thousands of years, the sky was a sanctuary of stability, a grand machine that hummed with a quiet, eternal music, providing a sense of meaning to the fragile inhabitants of a small, rocky world. As the tools of observation grew more sophisticated, transitioning from the naked eye to the brass quadrants of the Renaissance, and eventually to the massive glass mirrors of the modern era, the core assumption of a static universe remained largely unchallenged. Even Albert Einstein, the man who bent space and time with his mind, initially clung to the vision of a cosmos that stood still. In the early years of the 20th century, when he formulated his general theory of relativity, he found that his own equations suggested a universe that must either be expanding or contracting. Appalled by the idea of a restless cosmos, he introduced a mathematical patch, the cosmological constant, to force the universe into a state of artificial stillness. This was the peak of human desire for a world that did not change, a reality that could be mapped and mastered once and for all. That stillness was shattered in the late 1920s by a man standing on the cold, windswept summit of Mount Wilson in California. Edwin Hubble, peering through the 100-inch Hooker telescope, realized that the distant spiral nebulae were not merely clouds of gas within our own Milky Way, but entire islands of stars located millions of light-years away. More importantly, he observed that the light from these distant galaxies was shifted toward the red end of the spectrum. This redshift was the unmistakable signature of recession. The islands of stars were fleeing from us, and the farther away they were, the faster they moved. The static pond of the ancients vanished in an instant, replaced by a surging, expanding ocean of space-time. The universe was not a fixed stage. It was an inflating fabric, a dynamic and growing entity that had a definitive beginning in a hot, dense flash of light. From this revelation rose the ΛCDM model, the triumphant standard model of cosmology that would dominate the mid to late 20th century. This was the invisible cathedral of our scientific understanding, a structure of immense mathematical beauty that appeared to explain almost everything we saw in the deep dark. This model rested upon two mysterious and unseen pillars, dark matter and dark energy. Dark matter was the silent architect, the invisible glue that provided the extra gravitational pull needed to hold galaxies together. Without its hidden mass, the spinning wheels of stars would have flown apart like loose mud from a bicycle tire. Dark energy was the opposite force, a repulsive pressure that resided in the very fabric of empty space, pushing the universe to expand at an ever-accelerating rate. Together, these two substances accounted for roughly 95% of the total energy and matter in the cosmos. Though no human had ever seen, touched, or measured a single particle of dark matter, or a single wave of dark energy, we accepted their presence because the mathematics demanded them. The ΛCDM model was so successful at predicting the distribution of galaxies and the faint cold afterglow of the Big Bang, the cosmic microwave background, that it moved beyond the realm of mere theory and into the realm of dogma. We believed we had mastered the history of time itself. In the closing decades of the 20th century and the opening years of the 21st, a sense of supreme hubris settled over the scientific community. We spoke with absolute certainty about the first 3 minutes of existence, describing the nucleosynthesis of light elements with the confidence of eyewitnesses. We mapped the epoch of recombination, roughly 380,000 years after the beginning, when the universe finally cooled enough for atoms to form and light to travel freely. We calculated the exact window of the cosmic dawn, predicting that the first stars would ignite roughly 200 million to 400 million years after the initial expansion. According to our grand blueprint, these first stars would be massive, short-lived giants that would eventually cluster into small, chaotic and dim protogalaxies. These fragile ancestors would then merge over billions of years, slowly growing into the majestic spiral and elliptical structures we see in our local neighbourhood today. We believed that the early universe was a place of slow, gradual assembly, a primordial soup that took vast eons to cook into anything substantial. We had the timeline down to a decimal point. We had the physics of gravity and dark matter locked in a tight embrace. We were simply waiting for a telescope powerful enough to confirm the details of our brilliance, to photograph the small, messy seeds of the first galaxies exactly where we said they would be. We did not expect to find that the cathedral was built on sand, or that the pillars of dark matter and dark energy might be placeholders for a reality we had completely failed to imagine. The map was finished, or so we thought, until the golden eye of the sentinel opened and showed us a sky that refused to obey our rules. Before the golden mirrors were ever unfurled in the deep dark, before the first infrared photons were captured by the sentinel at the second Lagrange point, the grand cathedral of cosmology had already begun to groan. The fractures were not obvious at first. They were subtle, hairline cracks that appeared in the high vaulted ceilings of our theories, often dismissed as minor errors or the inevitable noise of imperfect instruments. For decades, we had leaned upon the standard model with the absolute confidence of a builder who trusts his level and his plumb line. But as our measurements grew more precise, as our telescopes became more sensitive, and as our mathematical models reached for a higher degree of certainty, a disturbing truth began to emerge. The universe was no longer agreeing with itself. The primary source of this unease lay in the measurement of the expansion of space, a value known as the Hubble constant. This number is the heartbeat of the cosmos, the fundamental rate at which the fabric of reality is stretching. To understand the history and the fate of the universe, one must know this value with absolute precision. However, when astronomers attempted to calculate this heartbeat, they found two different pulses. It was as if the universe possessed a dual nature that defied a single explanation. The first method of measurement involved looking back to the very beginning, to the faint cold afterglow of the Big Bang known as the cosmic microwave background. This light, which has been travelling since the universe was a mere 380,000 years old, provides a pristine snapshot of the primordial conditions of the cosmos. By applying the laws of the standard model to this ancient light, scientists could extrapolate forward in time to predict how fast the universe should be expanding today. This method yielded a specific value, a steady and predictable rhythm of roughly 67 kilometers per second for every megaparsec of distance. For a time, this number was the gold standard, the foundation upon which the age of 13.8 billion years was calculated. But a second method, one that looked at the modern local universe, told a different story. By observing pulsating stars known as Cepheid variables and the brilliant explosions of Type I supernovae in nearby galaxies, astronomers could measure the expansion rate directly. This cosmic distance ladder allowed them to gauge the speed of the receding galaxies with remarkable clarity. Yet, every time they climbed this ladder, they arrived at a different number, roughly 73 kilometers per second per megaparsec. A difference of 6 units might seem trivial to the uninitiated, a mere rounding error in the vastness of the infinite. But in the world of precision cosmology, this gap was a chasm. It was a statistical impossibility that both numbers could be correct if our map of the universe was accurate. As the years passed, and the data from missions like the Planck satellite and the Hubble Space Telescope became more refined, the gap did not close. Instead, it widened. The error bars shrank, but the two values remained stubbornly apart, staring at each other from across a void of misunderstanding. This was the Hubble tension, the first definitive sign that the cathedral of logic was settling on a foundation that was far less stable than we had assumed. It was as if we were holding two different maps of the same mountain range. The first map, drawn from the perspective of an ancient traveller who had seen the mountains when they were mere hills, predicted a certain path. The second map, drawn by a modern surveyor standing at the base of the peaks, showed a landscape that was far more rugged and expansive than the first map allowed. When the two maps were laid side by side, the rivers did not line up. The peaks were in the wrong places, and the trails led into empty air. The terrain of reality was refusing to obey the lines we had drawn upon the page. This tension created a growing crisis of faith among the architects of the invisible. Some argued that the problem lay with the instruments, that perhaps the Cepheid stars were not the reliable standard candles we believed them to be, or that some unknown systematic error was haunting the data of the early universe. Others began to whisper of more radical possibilities. They suggested that perhaps dark energy was not a constant force, but something that changed over time, a phantom energy that pushed the universe harder as it aged. Some even proposed the existence of a new form of matter, or a fundamental flaw in Einstein's theory of general relativity when applied to the vast scales of the cosmos. The atmosphere in the halls of physics became one of quiet, mounting dread. We were like sailors who had navigated by the stars for centuries, only to realize that the stars themselves were shifting in ways our charts could not predict. The standard model, which had once felt like an unshakable truth, began to feel like a beautiful but brittle shell. We were waiting for a sign, a piece of evidence that would either mend the fractures or shatter the shell entirely. We looked to the horizon, to the coming era of the James Webb Space Telescope, hoping that its superior vision would resolve the tension and bring the two maps into alignment. We hoped that by seeing further and more clearly than ever before, we would find the missing piece of the puzzle that would make the cathedral whole again. We did not realize that the Sentinel would not bring peace, but a revelation that would turn the tremors of the Hubble tension into a full-scale earthquake, threatening to bring the entire structure of our reality crashing down. The journey of the Golden Sentinel began not in the silence of space, but on a pillar of fire that tore through the heavy atmosphere of Earth. Folded into the cramped fairing of an Ariane 5 rocket, the James Webb Space Telescope was a masterwork of human ingenuity compressed into a space no larger than a small room. It was a hibernating titan, a complex architecture of glass, gold, and graphite waiting for the touch of the vacuum to begin its metamorphosis. As the rocket shed its stages and the blue marble of home receded into the distance, the machine was cast into the deep, beginning a lonely voyage toward the second Lagrange point. Once released into the absolute isolation of the void, the telescope began a mechanical ballet of terrifying complexity. This was an origami of the infinite. Over the course of several weeks, the machine slowly unfurled itself, a process governed by 344 separate mechanical points of failure. In the history of exploration, no machine had ever been asked to perform such a delicate sequence of movements without the possibility of human intervention. If a single motor seized, if a single cable snagged, or if a single latch failed to click, the mission would end as a silent multi-billion-dollar monument to failure. The first movement was the deployment of the sun shield, a structure of 5 specialized polymer layers, each as thin as a human hair and the size of a tennis court. This silver sail stretched out to create a thermal barrier of unprecedented efficiency. On the sunward side, the heat of the sun and the reflection of the Earth radiated with a ferocity that could boil water. Yet mere centimeters away, on the shadowed side of the shield, the temperature plummeted toward the absolute stillness of the void, reaching a staggering minus 233 degrees Celsius. This extreme cold was not a luxury. It was a fundamental requirement. To see the faintest heat signatures from the beginning of time, the telescope itself had to be colder than the very light it sought to capture. Then came the primary mirror, a vast basin of 18 hexagonal segments made of beryllium, each coated in a layer of gold only a few hundred atoms thick. These segments moved with the precision of a ghost, adjusted by tiny actuators that could shift the mirrors by a fraction of the width of a human hair. They clicked into a single, seamless eye, 6.5 meters across, designed to act as a gravity-defying bucket for light. This golden surface was tuned to the infrared, the long wavelength radiation that carries the secrets of the most distant reaches of space-time. The necessity of infrared vision was born from a fundamental barrier in the history of the cosmos. For hundreds of millions of years after the Big Bang, the universe was shrouded in a thick, suffocating fog of neutral hydrogen gas. This was the cosmic dark age, a period of absolute obscurity where the first stars began to ignite in the shadows. To a telescope operating in visible light, this era is an impenetrable wall. The neutral hydrogen absorbs and scatters shorter wavelengths, acting as a primordial mist that hides the birth of the first structures. However, infrared light, longer, more patient, and more resilient, possesses the ability to slip through the gaps in this hydrogen shroud. The James Webb Space Telescope was engineered to be the ultimate time machine, reaching into the abyss to catch photons that have been travelling for 13.5 billion years. These photons were born in the hearts of the very first suns, screaming into the void when the universe was a mere 3% of its current age. As these ancient messengers travelled across the expanding desert of space, the fabric of the universe itself stretched them. Their once brilliant ultraviolet and visible light was pulled and lengthened, reddening over the eons until it shifted into the infrared spectrum. This process, known as a redshift, turned the history of the universe into a heat signature that only a golden eye in the deep cold could perceive. As the telescope reached its final destination, and the instruments were calibrated to a degree of precision that defies common experience, it began to stare into the darkest patches of the sky, areas that appeared empty to every instrument that had come before. It was looking for the first light, the moment the cosmic fog began to lift, and the first galaxies began to assemble from the cooling embers of the creation. The world waited in a state of suspended breath, expecting to see the faint chaotic flickers of a universe in its infancy. Instead, as the data began to flow back across the million-mile void to the receiving stations on Earth, the Sentinel revealed a reality that no model had predicted. It did not find a world of slow, stumbling growth. It found a universe that had hit the ground running, birthing giants in the dark that should not have existed for billions of years to come. The time machine had worked perfectly, but the history it revealed was one we did not recognize. The moment the first deep field image flickered onto screens across the globe, the air in the command centers and living rooms alike seemed to vanish. There was a collective gasp, a sharp intake of breath that united the world in a single heartbeat of awe. We had been told to expect a glimpse into the past, but we were not prepared for the sheer, overwhelming density of what stared back at us. A patch of the sky no larger than a single grain of sand held at arm's length against the night was revealed to be a riot of colour and form. It was not a void, it was a tapestry. Where we expected to find a few lonely primitive smudges of gas, the supposed seeds of the first stars, we found a sky crowded with thousands of jewel-like galaxies, each a swirling city of billions of suns. These were not the faint, chaotic embers of a dying fire. They were intricate, complex structures, spirals with delicate arms of blue stars, elliptical glows of ancient red suns, and distorted arcs of light bent by the immense gravity of foreground clusters. The darkness was an illusion. The Sentinel had looked through the keyhole of the universe and found a palace of light where we had expected a desert. This was the first true testament to the power of the infrared eye, a revelation that the early universe was not a quiet, empty room, but a crowded theatre of creation. The secret to this vision lies in the physics of the ghost of light. To understand what the telescope saw, one must understand the journey of the photon. Light is not a static thing. It is a traveller that is subject to the whims of the road it walks. As these photons were birthed in the hearts of the first stars, they began their journey as high-energy ultraviolet and visible light. But the road they travelled, the very fabric of space-time itself, was not stationary. For 13.5 billion years, as these photons raced toward us at the speed of light, the universe was expanding. This expansion does not merely move galaxies apart, it stretches the space between them. As the light travelled through this inflating medium, the waves themselves were pulled apart. A tight blue wave of light becomes a long, relaxed red wave. This is the process of redshift, a cosmic stretching that turns the history of the universe into a spectral ghost. By the time these photons reached the golden mirrors at the second Lagrange point, they had been stretched so far that they had slipped out of the visible spectrum entirely, becoming the heat signatures of an era long since past. They are the ghosts of light, carrying the likeness of stars that may have died billions of years ago, yet their image remains preserved in the infrared. These photons are the ultimate messengers. They have crossed the vast, expanding deserts of the void, surviving the gravitational tug of dark matter and the interference of cosmic dust. They have travelled through epochs where the first atoms were forming, through the era where the first galaxies were colliding, and finally through the modern age where a curious species on a small blue planet built a machine specifically to catch them. When they finally struck the 18 golden hexagons, they ended a journey of nearly 13.8 billion years. The data they carried was a shock to the system. The Standard Model had predicted that these early galaxies should be small, dim, and disorganized. We believed that in the first few 100 million years, gravity would only have had enough time to pull together small clumps of matter. We expected to see the toddlers of the cosmos. Instead, the red-shifted light revealed adults, mature, massive galaxies that contained as much mass as our own Milky Way, existing at a time when the universe was still in its infancy. The ghost of light had brought a message we were not prepared to hear. It spoke of a universe that was far more efficient at building suns and systems than our equations allowed. It spoke of a beginning that was not a slow crawl from the dark, but a sudden, brilliant eruption of complexity. The jewel-like galaxies in the deep field were not just beautiful, they were impossible. They stood as silent, shimmering rebukes to our certainty, suggesting that the timeline of the cosmos was either much longer than we believed, or that the laws governing the assembly of matter were far more potent than we had ever dared to write in our journals. The messengers had arrived, and they had brought with them the news of a revolution. This revolution manifested as a series of distinct glowing anomalies identified in the very first deep field surveys. These were not the faint, fragmented whispers of light that theorists had spent decades preparing to see. Instead, they were massive, luminous anchors of matter situated in an era where the universe was between 500 million and 700 million years old. According to the established cosmological timeline, this period should have been the dawn of the first light, a time when gravity was only just beginning the agonizingly slow process of herding primordial gas into the first primitive star clusters. Instead, the infrared sensors of the Sentinel detected galaxies containing as much stellar mass as the modern Milky Way, existing at a time when the universe was a mere 3 to 5% of its current age. The shock within the astronomical community was visceral, a tremor that shook the very foundations of the discipline. To find a galaxy harbouring 100 billion suns so soon after the beginning is akin to walking into a hospital nursery and discovering a fully grown 6-foot-tall adult sitting among the infants in their cradles. It is a biological and physical impossibility within the framework of any expected growth cycle. In our established models, galaxies are the product of a long hierarchical struggle. They are supposed to grow through a series of patient mergers, small, chaotic clumps of gas and dark matter gradually colliding and coalescing over billions of years to form the majestic structures of the modern era. But these objects, which have earned the moniker of universe breakers, appeared to have skipped the childhood of the cosmos entirely. They emerged into the light already ancient and already massive. The spectra of their light suggested they were teeming with old red stars, implying that they had been forming matter with an efficiency that defies every known law of star formation. These objects were not just massive, they were impossibly compact. They appeared to pack the mass of a modern, sprawling galaxy into a volume of space 30 times smaller than our own Milky Way. This incredible density creates a gravitational environment that our current simulations simply cannot replicate. To build such a structure in so short a window of time, nearly every atom of hydrogen available in the local primordial environment would have had to be converted into stars with almost 100% efficiency. In the reality we thought we understood, star formation is a messy, wasteful and self-limiting process. As the first stars in a cloud ignite, their intense radiation and the eventual shock waves of their supernova deaths blow the remaining gas away, preventing further collapse and slowing the growth of the galaxy. It is a system of cosmic checks and balances, yet these early giants seem to have bypassed these feedback loops entirely, cooling and collapsing with a speed and a ferocity that suggests our understanding of the thermal history of the early universe is fundamentally broken. They represent a wall of data that has crashed against the shores of our established theories with the force of a tidal wave, leaving the architects of the standard model struggling to find a foothold. The presence of these giants creates a profound problem of timing. If the Big Bang occurred 13.8 billion years ago, and if the first stars did not ignite until 200 million years after that, there is simply not enough time for gravity to have moved that much matter across those distances to create these massive cities of stars. Gravity is a patient force. It moves at the speed of light, and its influence over the vast, expanding distances of the early universe is limited by the density of the medium. The ΛCDM model dictates a specific speed for the assembly of the large-scale structure of the universe. These observations suggest that the universe was building its most grand monuments, while the blueprints were still being drawn. This structural barrier in our understanding of reality is not a minor discrepancy that can be solved by adjusting a few variables in a computer program. It is a fundamental mismatch between the observed terrain and our theoretical maps. If these galaxies are as massive as their light implies, then the dark matter halos that host them must also be far more massive than we believed possible for that epoch. This pushes the problem further back, into the very nature of dark matter itself and the conditions of the primordial soup from which all things emerged. We're forced to ask if our invisible friend, dark matter, possesses properties that allow it to clump far faster than our cold dark matter theories allow. The atmosphere in the halls of physics has shifted from excitement to a haunting realization that the textbooks may need to be burned. The universe breakers stand as silent, shimmering rebukes to our collective certainty. They suggest that we have either fundamentally misunderstood the rate at which time passes on a cosmic scale, or we have failed to identify a primary force that governed the early assembly of the world. The wall of data is solid, and it is growing. With every new deep field observation, the Sentinel finds more of these impossible giants, each one a testament to a history we did not write, and a reality we are only just beginning to perceive. The nursery is full of adults, and the old rules of growth no longer apply. A profound and heavy silence has descended upon the halls of theoretical physics, a quietude born of shock and the slow, grinding realization that the foundation of our cosmic history has been moved. For decades, the mathematicians and theorists were the masters of the narrative, weaving a complex and beautiful tapestry of equations that explained the birth of every star and the assembly of every galaxy. They worked within the rigid confines of the ΛCDM model, a framework that dictated a specific measured pace for the development of the universe. But as the data from the golden eye continues to pour in, those equations have begun to stutter and fail. The theorists now stand before a wall of impossibility, staring at a reality that their math simply cannot account for. At the heart of this crisis is the fundamental problem of time. Gravity, the weakest of the four fundamental forces, operates with a patient and rhythmic persistence. It is the sculptor of the cosmos, but it is a sculptor that requires eons to finish its work. In the early universe, matter was spread out in a nearly uniform soup of hydrogen and helium. For gravity to create a galaxy as massive as the ones the telescope has revealed, it must first overcome the massive outward pressure of the expanding universe. It must pull atoms together into clouds, clouds into stars, and stars into the vast spinning cities of light we call galaxies. According to the laws of physics as we have understood them for a century, there simply were not enough years between the Big Bang and the observation of these giants for such a monumental task to be completed. The math is unyielding. To build a galaxy of 100 billion suns within 500 million years of the beginning, the universe would have had to work with a speed and an efficiency that borders on the miraculous. It would be like watching a forest grow from seeds to ancient towering oaks in the span of a single afternoon. The speed of light and the strength of the gravitational constant act as a cosmic speed limit, a governor on how fast matter can move and how quickly it can collapse. The universe breakers suggest that this speed limit was either ignored or that the governor was never there. The theorists find themselves trapped in a chronological vice. The universe is either much older than 13.8 billion years, or gravity possessed a hidden, ferocious strength in the dawn of time that has since vanished from the world. This realization has turned the once vibrant debates of the scientific community into a somber reckoning. The textbooks that served as the holy scriptures of cosmology for 2 generations are suddenly being viewed with a mixture of nostalgia and suspicion. In university lecture halls and high-level research symposia, the atmosphere is thick with the metaphorical scent of burning paper. The old world, where we could predict the ignition of the first stars to within a few million years, has been replaced by a landscape of profound uncertainty. We are witnessing the death of a paradigm. The structural barrier we have encountered is not just a lack of data, but a failure of our very capacity to model the infinite. The gears of the cosmic clock we thought we had mastered are spinning at a rate that defies our most sophisticated simulations. Theorists stand at their blackboards, their hands stilled by the weight of the contradiction. They look at the images of mature red-shifted galaxies, and then at their own derivations of dark matter density and primordial cooling rates, and the 2 realities refuse to merge. The bridge between the early universe and the modern era has collapsed. If the standard model cannot explain these giants, then the standard model is not merely incomplete, it is a map of a different universe entirely. This is the structural impossibility that haunts the modern astronomer, the realization that our most cherished theories of how the world began are fundamentally incompatible with the world as it actually exists. The silence of the theorists is not one of defeat, but of a terrifying, exhilarating transformation. They are standing at the edge of a precipice, looking into a void where the old rules of gravity and time no longer apply. The wall they have hit is solid, made of the undeniable silver and gold of observed data. It is a barrier that cannot be bypassed with clever mathematical tricks or minor adjustments to the cosmological constant. To move beyond this wall, they must be willing to dismantle the cathedral they spent their lives building. They must consider radical possibilities, that the expansion of space is not constant, that gravity changes its nature over vast distances, or that the very vacuum of space contains energies we have yet to name. The realization is setting in that we are not just refining our understanding, we are beginning again. The ink of the old world is still wet, but the pages are already being turned. The crisis of the universe breakers has revealed that our intellect, while capable of building machines that can see across 13 billion years, is still humbled by the sheer, stubborn mystery of the thing it observes. We have found a wall, and in doing so we have discovered that the universe is not a clock that follows our rules, but a wild and ancient sea that we are only just beginning to chart. The math has failed, the models have shattered, and in the resulting silence, the true work of discovery begins. The shadow of Albert Einstein looms over this wreckage of modern theory, his presence a ghost that haunts every attempt to reconcile the impossible giants with the laws of the known. In the early years of the 20th century, specifically 1917, Einstein looked at his own equations of general relativity and saw a universe that refused to stand still. The math insisted that the cosmos must either be collapsing under its own weight or flying apart into the void. To preserve the ancient dream of a static, eternal universe, he introduced a mathematical ghost into his work, the cosmological constant, represented by the Greek letter lambda. This was a repulsive force inherent to the vacuum of space itself, a hidden energy that pushed back against the pull of gravity to maintain a perfect, frozen balance. When the observations of 1929 proved that the universe was indeed expanding, Einstein famously discarded the cosmological constant, labelling it his greatest blunder. He believed he had failed to trust the purity of his original equations. Yet, as the golden sentinel at the second Lagrange point reveals a history that defies our current timeline, that supposed blunder is being resurrected as perhaps his most profound intuition. We have come to realize that empty space is not truly empty. It possesses a weight, a tension, and a latent energy that dictates the expansion of all things. The ghost of lambda has returned to the center of the stage, no longer as a tool to keep the universe still, but as the primary driver of its accelerating flight. This resurrection of Einstein's intuition forces a harsh light upon the other invisible pillar of our cathedral, dark matter. For nearly half a century we have operated under the dark matter paradigm, treating this unseen substance as the silent architect of the cosmos. We observed that galaxies spin far too fast for the visible stars and gas to hold them together. Without some extra invisible mass, they would fly apart like loose sand on a spinning wheel. To fix the math, we invented an invisible friend. We posited that the universe is filled with a cold, dark matter that does not interact with light, a substance that makes up roughly 85% of all matter in existence. But as the James Webb Space Telescope reveals massive galaxies that formed in a heartbeat, we must ask if our invisible friend is a true physical entity or merely a placeholder for a physics we have yet to grasp. Dark matter has become the ultimate ghost in the machine of the universe. It is an unseen force that dictates the movement of stars and the clustering of galaxies, yet it remains forever out of reach of our most sensitive terrestrial instruments. We have built massive detectors in the hearts of mountains and deep underground in abandoned mines, waiting for a single particle of dark matter to reveal itself. Thus far, this silence from these experiments has been absolute. The discovery of the universe breakers suggests that the ghost in the machine might be far more complex than a simple cloud of invisible particles. If these early galaxies grew so large so quickly, then the dark matter scaffolding that supported them must have behaved in ways our models cannot explain. It suggests that gravity itself might not be the constant, unchanging law we believe it to be. Perhaps across the vast, lonely stretches of the deep cosmos, or in the high-density environment of the early universe, the rules of attraction were different. We are forced to consider the radical possibility that dark matter is an illusion, a symptom of a fundamental flaw in our understanding of gravity on a galactic scale. This is the crisis of the genius. We are caught between the brilliance of Einstein's relativity and the stubborn reality of the observed light. If the cosmological constant is not a constant, or if dark matter is not matter at all but a misunderstanding of the fabric of space, then the entire history of the universe must be re-evaluated. The ghost of the cosmological constant and the phantom of dark matter may be two sides of the same coin, names we give to our ignorance of the true energy of the vacuum. The theorists, once so confident in their dark matter simulations, now watch as their digital universes fail to produce the giants that the Sentinel sees with ease. They are beginning to wonder if we have been trying to solve the wrong puzzle. We have spent decades looking for a particle that might not exist, while the answer might lie in the very geometry of spacetime that Einstein first described. The ghost in the machine is whispering a new truth, that the universe does not care for our categories of matter and energy. It follows a deeper logic, a hidden symmetry that allows for the impossible to become manifest. As we stand before the wall of impossibility, the legacy of Einstein offers both a warning and a way forward. It reminds us that the most profound truths often hide behind what we perceive as errors. The cosmological constant was a blunder only if the goal was a static universe. But as a description of the energy of the void, it may be the key to the entire mystery. We are currently in a state of scientific haunting, pursued by the ghosts of theories that no longer fit, and the phantoms of matter we cannot find. The only way to find peace is to be as bold as the man who first dared to bend the light, and to accept that the machine of the universe may be operated by forces that require a completely new language of reality. The Sentinel has shown us the giants. Now we must find the courage to name the power that built them. The naming of this power has brought the scientific world to a state of open, intellectual warfare, a conflict centered on the very heartbeat of the cosmos known as the Hubble tension. This is not a mere academic disagreement. It is a fundamental schism in our understanding of how space-time behaves. At its core, the tension is a clash between the past and the present, a war between two different ways of measuring the expansion of the universe. It is a rope being pulled from both ends by two different eras of time, and with the arrival of the data from the Golden Sentinel, that rope has finally begun to snap. On one side of this tug-of-war are the cosmologists who look back to the very beginning, to the cosmic microwave background. This is the oldest light in existence, a fossilized imprint of the universe, as it was a mere 380,000 years after the Big Bang. By using the Planck satellite to map this ancient glow with exquisite precision, scientists can see the seeds of everything that would eventually become galaxies and stars. They feed this data into the standard model, the ΛCDM framework, and use it to predict how fast the universe should be expanding today. Their result is a steady rhythmic pulse of roughly 67 kilometers per second for every megaparsec of space. This number is the anchor of the early universe camp, a value derived from the purity of the primordial fire. On the other side are the astronomers who measure the expansion of the modern universe directly. They use a method known as the cosmic distance ladder, relying on standard candles, objects whose intrinsic brightness is known. By observing pulsating stars called Cepheid variables and the cataclysmic explosions of Type I supernovae, they can calculate exactly how far away a galaxy is and how fast it is receding from us. For years, this camp, led by the observations of the Hubble Space Telescope, has consistently arrived at a different number, roughly 73 kilometers per second per megaparsec. For a long time, the hope was that this discrepancy was simply a mistake. Perhaps the Cepheid stars were not as reliable as we thought, or perhaps there was some hidden bias in how we interpreted the light of supernovae. Many expected that when the James Webb Space Telescope turned its superior infrared gaze toward these same stars, the tension would vanish. We thought the new data would show that the modern measurements were slightly off, bringing them back into alignment with the 67 predicted by the early universe. Instead, the Sentinel has done the opposite. With its ability to see through the dust that sometimes obscured the vision of previous telescopes, the James Webb Space Telescope has confirmed the modern measurements with terrifying clarity. It has looked at the same Cepheid stars and found that the 73 is not an error. It is a reality. The two ends of the rope are moving further apart, and the standard model, which serves as the cord connecting the beginning of time to the present day, is being stretched beyond its breaking point. The tension has reached a level of statistical significance that scientists call 5 sigma, a threshold where the chance of the disagreement being a fluke is less than 1 in 3.5 million. The snapping of this rope represents a crisis of the highest order. It suggests that our mathematical bridge from the Big Bang to the present is missing a fundamental piece of physics. The universe is expanding faster today than the laws of the early universe say it should be. To fix this, theorists are being forced to propose radical, almost desperate ideas that challenge the very nature of reality. One such proposal is the existence of early dark energy. This theory suggests that in the first few 100,000 years of existence, before the first atoms even formed, there was a sudden violent pulse of repulsive energy. This whoosh would have kicked the expansion of the universe into a higher gear, changing the initial conditions in a way that would allow the modern expansion rate to be higher without contradicting the ancient light of the cosmic microwave background. It is a ghost force, a temporary surge in the energy of the vacuum that appeared, did its work, and then vanished into the shadows of history. Another even more radical possibility is that gravity itself is not the constant universal law we believe it to be. This theory suggests that gravity might behave differently across the vast, lonely distances between galaxy clusters, or that its strength has evolved over the billions of years of cosmic time. If gravity weakens as the universe grows larger and more empty, it would allow the expansion to accelerate in ways the standard model cannot predict. This would mean that Einstein's masterpiece of general relativity is not the final word on the movement of the heavens, but merely a local approximation of a much deeper and more complex set of rules. The Hubble tension has turned the study of the cosmos into a hunt for new physics, a term that describes the unknown laws that exist beyond the boundaries of our current textbooks. The data from the Sentinel has acted as a catalyst, transforming a quiet discrepancy into a full-scale revolution. We're no longer just measuring the universe. We're watching our old definitions of space, time, and energy crumble. The rope has snapped, and in the resulting recoil, we are being forced to confront a cosmos that is far more dynamic, far more restless, and far more mysterious than the clockwork machine we once imagined. The war of the measurements is not just about a number. It is about the soul of the universe, and the realization that the truth lies in a reality we have yet to name. In the quiet, blue-lit hours of the early morning, the search for a new name for reality falls upon the shoulders of a new generation of researchers. These are the young astronomers, many of them in the dawn of their own careers, who sit before flickering monitors in darkened offices, sifting through the raw streams of data transmitted from the second Lagrange point. For them, the James Webb Space Telescope is not just a triumph of engineering, it is a source of profound existential vertigo. As they plot the luminosities and redshifts of these impossible giants, they find themselves caught in a harrowing internal conflict. On one hand, There is the soaring exhilaration of a world-changing discovery, the realization that they are the first humans to ever lay eyes on the true face of the primordial deep. On the other, there is a cold, gnawing fear, the terror of being fundamentally, publicly and catastrophically wrong. The weight of this revelation presses against the chest of every researcher who identifies a universe breaker. When a young postdoctoral student stares at a spectral line indicating a massive mature galaxy at a redshift of 10 or 11, their first instinct is not to celebrate but to doubt. They check the calibration of the instruments, they rerun the software, they search for ghosts in the optics or artifacts in the sensors that might explain away the anomaly. To claim that the standard model of the universe is broken is an act of supreme scientific audacity. It is to challenge the work of the giants who came before, to tell the architects of the ΛCDM model that their invisible cathedral is built upon a misunderstanding of time itself. These scientists are like explorers standing on the edge of a new continent, realizing with a sinking heart that the maps they brought with them are useless. They have sailed across the ocean of the cosmic dark ages, guided by charts that promised a shoreline of small scattered islands of gas. Instead, they have found a land of towering mountains and vast, sprawling cities of stars. The parchment of their education, filled with the elegant lines of hierarchical galaxy formation, is now a series of blank spaces. The terrain of the early universe as revealed by the golden eye does not care for the boundaries or the pathways they were taught to follow. It is a wild, untamed reality that demands a new language, a new geometry, and a new humility. The process of reconstruction is slow and often painful. It involves the public admission of ignorance, a vulnerable state for a species that prides itself on its mastery of the heavens. In peer-reviewed journals and at international symposia, the debate is no longer about the details of the model, but about the survival of the model itself. There is a specific kind of beauty in this struggle. It is the beauty of a mind being forced to expand to accommodate a larger truth. The young astronomers who find these galaxies are the first to admit that they do not know how they got there. They are the first to say that the math fails, that the simulations crash, and that the universe is stranger than we were permitted to suppose. This admission is the true engine of discovery. It is the moment when the ego of the scientist is eclipsed by the majesty of the subject. They are learning to live in the tension between the data and the theory, refusing to look away from the contradiction. Every time they confirm the mass of a galaxy that should not exist, they are tearing down a piece of the old world to make room for the new. They are the cartographers of the impossible, sketching the outlines of a cosmos that grew with a ferocity and a speed that defies our current understanding of gravity. The fear of being wrong slowly gives way to the realization that being wrong is the most exciting thing that can happen in science. If the old maps were perfect, there would be no more worlds to find. If the standard model were the final truth, the story of the universe would be a closed book. But the universe breakers have ripped the pages out, offering a glimpse of a much grander and more mysterious narrative. The young researchers find themselves in a state of grace, standing at the precise moment when human knowledge ends and a new era of understanding begins. They are the ones who must find the courage to say that the wall they have found is not a dead end, but a door. This reconstruction of reality is a collective labour, a slow-motion revolution that involves thousands of minds working in concert. It is a process of admitting that we are still children in a very old and very large house, and that we have only just begun to explore the rooms in the basement. The silence of the theorists is being replaced by the vibrant, messy, and urgent work of the observers. They are piecing together a new history of the light, one that accounts for the giants in the nursery and the accelerating pulse of the expansion. It is a beautiful, agonizing rebirth of cosmology, driven by the simple, stubborn fact that the stars are there, and they are telling us a story we never expected to hear. The Sentinel has done its job. It has shown us the limits of our imagination, and now the human element must take the lead, stepping into the dark with nothing but the data and the will to understand. The presence of these impossible giants has forced a radical re-evaluation of the cosmic calendar. If the clock began 13.8 billion years ago, the mathematics of galaxy formation simply refuses to reconcile with the reality captured by the golden mirrors. Consequently, some voices within the scientific community, once relegated to the fringe, are moving toward the centre of the debate, suggesting that the universe is significantly older than we have dared to believe. One controversial proposal suggests a time frame nearly double our current estimate, roughly 26.7 billion years. In such a vast expanse of time, the mystery of the mature galaxies evaporates. Gravity would have had the necessary eons to gather the primordial gas and forge the massive cities of stars that the Sentinel now observes. This is not merely a change in a number, it is a fundamental shift in the scale of our existence, implying that we have been living in a house much older and more seasoned than our records indicated. Beyond the simple expansion of time lies the possibility that the Big Bang was not the definitive birth of all things, but rather a transition. This is the theory of the Big Bounce. It posits that our universe exists in a state of eternal recurrence, a rhythmic cycle of expansion and contraction. In this view, the beginning we perceive was merely the moment a previous universe collapsed under its own weight, reaching a point of maximum density before rebounding outward once more. The massive galaxies found by the James Webb Space Telescope could be the echoes of this previous incarnation, structures that formed more rapidly because the seeds of their existence were already sown in the embers of the world that came before. We are no longer looking at a singular event, but a single breath in a cosmic respiration that has no beginning and no end. The wall of impossibility also hints at a reality where our observable universe is but a small, shimmering bubble in a much larger and stranger sea. This is the realm of eternal inflation, where the vacuum of space is constantly birthing new universes, each with its own laws of physics and its own speed of light. In this vast, foaming multiverse, the discrepancies we observe, the Hubble tension and the universe breakers, might be the result of our bubble interacting with the currents of that larger ocean. We are beginning to see our entire history, from the first flash of light to the present day, as a local phenomenon, a tiny pocket of order within an infinite and chaotic expanse. The wall we have encountered is the edge of our current perception, the point where the specific rules of our bubble begin to fray and reveal the alien logic of the greater whole. This shifting understanding of the beginning inevitably alters our vision of the end. If the expansion of the universe is driven by a dark energy that is even more potent than we suspected, the fate of all things may be the Big Rip. In this scenario, the repulsive force of the vacuum grows so strong that it eventually overcomes the gravity holding galaxies together, then the electromagnetic bonds holding stars and planets, and finally the nuclear forces holding atoms themselves. Reality literally tears itself asunder, the fabric of space-time shredding until every particle is isolated in a lonely fragmented void. Conversely, if the universe follows the path of the Big Bounce, we may be headed for a big crunch, a slow and agonizing reversal where the expansion halts and the cosmos begins to fall inward, eventually vanishing back into the singularity from which it sprang. Most haunting is the prospect of the slow descent into eternal silence, the heat death of the universe. In this future, the expansion continues forever, pushing galaxies so far apart that they disappear from each other's view. One by one, the stars exhaust their fuel and flicker out. The red dwarfs, the last holdouts of the light, eventually fade into blackness. The black holes evaporate through Hawking radiation over trillions upon trillions of years, leaving behind nothing but a thin, cold soup of subatomic particles drifting in a darkness that is absolute and unchanging. This is the ultimate victory of entropy, a state where time itself loses its meaning because nothing ever happens again. The new data from the Sentinel does not yet tell us which of these ends is certain, but it has revealed that the path to that end is far more complex and far more terrifying than we had ever dreamed. We are travellers on a ship whose destination is unknown, navigating by the light of stars that shouldn't exist, in a sea that is far deeper than our maps ever allowed. The wall we have found is not just a barrier in space, it is a barrier in our understanding of the fate of time itself. As we look into the infrared glow of the first galaxies, we are looking at the evidence of a universe that does not care for our predictions, a cosmos that is as wild and unpredictable in its death as it was in its birth. Our search for the origin has led us to a confrontation with the infinite, and the answers we find will determine whether we are part of a singular flash of light or a permanent pulsing part of an eternal darkness. The golden eye remains open, a lonely sentinel at the edge of forever, staring into the deep infrared where the first light still echoes across the vastness of the void. This machine, a masterwork of beryllium and gold, continues to harvest photons that have travelled for 13.5 billion years, each one a fragile messenger from a world we thought we had mapped. But the maps have failed us. The cosmic irony of our search is that every time we reach for the ultimate answer, the universe responds with a deeper and more profound question. We built the James Webb Space Telescope to confirm the history of the light, to finalise the blueprints of the Standard Model, and to bring a sense of closure to the story of our origins. Instead, we found a wall that shattered our certainty and revealed the breathtaking arrogance of our supposed mastery. This wall is not a dead end, nor is it a sign that the search for truth is futile. It is a threshold. In the history of human thought, every great leap forward has been preceded by a crisis of the known. We are currently living through such a crisis, a beautiful and terrifying moment where the data from the stars is outstripping the capacity of our imaginations. The universe breakers, those mature giants standing in the nursery of time, are not errors of nature. They are invitations to a larger reality. They tell us that the universe is not a simple machine that follows a linear path from dust to stars. It is something far more resilient, far more creative, and far more mysterious. The wall we have found is merely the edge of our current perception, a boundary that marks the end of the old world and the beginning of a new, more complex understanding of space and time. There is a haunting humility in this realization. We are a species of biological machines, born on a small, rocky world orbiting a common star in the quiet suburbs of a galaxy that shouldn't be as it is. We are composed of the very atoms that were forged in the hearts of the stars we now observe. When we look through the golden mirrors of the Sentinel, we are not just looking at distant objects, we are looking at our own ancestry. We are the universe trying to understand itself, a way for the cosmos to gain a sense of its own history. The fact that we have reached a point where we can identify the flaws in our own models is a testament to the power of the human spirit. Our intellect may be humbled by the giants in the dark, but our capacity for wonder remains undiminished. The echo of the first light continues to ripple through the expanding fabric of the cosmos, carrying with it the secrets of the beginning and the hints of the end. We may never find a final, unchanging map of the infinite. We may discover that the expansion of the universe is driven by energies we can never touch, or that our bubble of reality is just one of an infinite number of seas. But the lack of a final answer does not rob the journey of its meaning. The cosmic irony is that the more we learn, the less we know, and yet we continue to look into the dark. We continue to build machines that can see through the fog of neutral hydrogen and reach back 13.8 billion years, driven by a hunger for truth that is as old as the stars themselves. As the James Webb Space Telescope orbits the second Lagrange point, 1.5 million kilometers from the pale blue dot of home, it serves as a monument to our curiosity. It has revealed that the universe is not only stranger than we suppose, but stranger than we can suppose. The Hubble tension, the early dark energy, the impossible maturity of the first galaxies, these are the cracks through which a new light is beginning to shine. We are standing at the door of a reality that we are only just beginning to perceive, a world where time may be a cycle, where gravity may be a variable, and where the vacuum of space is a reservoir of infinite power. The questions we ask are the only things that truly belong to us in this vast, shimmering darkness. Theories will rise and fall, the Standard Model may be replaced by a new cathedral of logic, and that cathedral too will eventually show its cracks. But the act of looking, the act of reaching into the abyss to catch a ghost of light, is what defines us. We are the architects of the invisible, the dreamers of the infinite, and the witnesses to a creation that is still unfolding in ways we cannot yet name. The wall is not there to stop us, it is there to remind us that there is always more to see. In the end, the legacy of our species will not be the answers we found, but the courage we showed in facing the unknown. We are a part of a cosmic respiration, a single pulse in a history that stretches across eons. As we sit on our tiny rock, watching the data stream back from the Golden Sentinel, we realize that the universe is not a puzzle to be solved. but a mystery to be experienced. The answers may change, the math may fail, and the models may shatter, but the search continues. We are the light of the universe looking back at its own beginning, and in that gaze we find the only meaning that matters. The sentinel has seen the giants, and the giants have told us that the story is just beginning. We step forward into the dark, not because we have the map, but because the questions are the only way home.